So one participant just mentioned that there was a problem with one of the YouTube videos with the slides not matching the audio. If you do notice that, please send me an email and we will see about correcting that. So that was true of the last lecture, and for that I think it's okay, because the last lecture I think it was a case of me giving both too little and too much information, where I gave you just enough so that you can't use the algebraic notation, probably. But hopefully it might help at some point if we do use more of the algebraic notation. But for the most part, people will be using, many people use the barcode, visual description, and that does, as we will see in our next example, that can be helpful to have the visual description. The algebra, if you want to go further, can be quite useful. But for those who want to ignore the algebra, you can ignore the last lecture for its many problems, including the technical ones. But if you did notice problems with any of the other lectures, please do let me know. So today we're going to take a look at the image application data. Oops, my pen went away. So we'll take a look at image data application in order to motivate the witness complexes. I put in too much preliminary information, so you probably won't get to witnesses until Wednesday. But we will discuss how to look at data with an example we looked at before, as well as the image data. And then we'll talk about creating complexes, doing a very, very quick review of the RIPs and the checks, and then also discussing the Voronoi, Delaunay triangulation, and alpha shapes a bit. So that will help motivate the witness complexes, and it also lets you know there's a number of different complexes out there which can be very helpful depending upon the size of your data and what it is you're trying to figure out. Everybody should have microphone rights if there's any questions. I thought I noticed some typing. Any questions? Okay. So I just wanted to quickly review the discriminative persistent homology of the brain network, and just to remind you that when we took a look at this, remember when we did the breast cancer data, it didn't look like the complex was all that interesting, but we only took a look at the patients who survived longer than 5 years. We didn't compare them to those who did not survive or those who never got breast cancer. And so one thing that we could do, even if you don't have any interesting homology, would be just to compare the different groups and to see how quickly the things persist. So the fact that for the ADHD, that the components, that you have multiple components for a longer period of time than for the other two groups, and for the pediatric control, you more quickly make connections. I mean, that can give you some information as well. So just because you don't see homology with your first look doesn't mean you should stop looking. You should think about other ways of looking at it. And that's one of the nice things about reading lots and lots of different applications that have nothing to do with what you're studying, because you might get ideas about how to look at that from other papers. So brain data, just talk about the rate of the persistence. So we're going to, most of these slides for the data is taken from a talk given by Gunnar Carlson in 2009. I've updated a little bit from 2012, and we're basically covering the applications to natural image statistics by De Silva, Ishkanov, Zamarodian, and Carlson. So basically, people like to study images. This is useful if you want to do image compression, or if you want to study how the brain processes images. So there's a variety of different ways of looking at images. Generally speaking, a typical camera uses tens of thousands of pixels. So you've got tens of thousands of pixels here. Forgot to turn on the pen again. You might just ignore the pen today. So we usually have tens of thousands of pixels. So each of these blocks is a pixel right here. And so it will have, we're going to do black and white pictures only. We could do color as well. In another paper, they analyzed depth. So they had a camera that just the color of the pixel would depend upon the depth. But here we're just doing a grayscale, nice black and white pictures, and so each pixel gives us a different grayscale thing. We're going to model the pixels with real numbers, so we're going to say each pixel has a real number corresponding to how white or how black or how gray it is. In reality, there's only 255 values, but sometimes actually throwing in and making your thing more continuous can actually be useful. So we will assume a continuous distribution, even though in reality it's not. With topology, it doesn't really matter because small perturbations aren't going to change our topology. So we do have this specter. Usually it's very large. And most, one of the things you can notice is that if you just take a random collection of pixels with random grayscales, you're probably not going to have a picture. So for example, this picture right here doesn't look to me like it's a real picture. Looks like a random collection of whites, grays, blacks, and various shades of gray. So we can imagine that if you were to study the shape of, actual images within, we'd actually be talking about, since we're assuming that each pixel is a real number, and if we've got 10,000 pixels, then we have 10,000 real numbers, so we're in R to the 10,000. But the space of actual images would probably be much less than that. And we would like to know what that dimension is, but it's still a very difficult problem. So instead of looking at that problem, we're going to look at a simpler problem. And that is looking at 3 by 3 patches. So that's still going to, so instead of taking a look at the entire, taking a look at this entire image, we're going to restrict ourselves to just a 3 by 3 patch. So we're just going to look at, say, this 3 by 3 patch right here. We can also take a look at this 3 by 3 patch right here, this 3 by 3 patch. We can take a look at all the 3 by 3 patches. Overlapping is just fine. So we'll take a look at many patches. Since they're 3 by 3, we get a vector in R to the 9, where each coordinate tells us in our pixel, medium gray, light gray, darker gray, so we'll get numbers for each of these. So we'll get 9 numbers for these. Most of the patches will actually be low contrast. So if you take a look at a picture, just go ahead and take a look at the screen. My picture, there's a 3 by 3 picture right here. That's a 3 by 3 pixel right here. But it's a rather boring 3 by 3 pixel because it's all white. It's very low contrast. And so if you try to study these 3 by 3 patches, I said pixel 3 by 3 patches, we want to throw out the boring ones because they will dominate. So most of them will be low contrast, they'll be boring, we don't want them to dominate our data, so we throw them out. So in the original study that did not use algebraic topology, they studied only high contrast patches. So we have 4.5 million high contrast patches obtained by this Dutch group of taking pictures, I think it was in the Netherlands. So we have 4.5 million patches, vectors in R9, so we have 4.5 million data points. Thus, we may want to use something less than the 4.5 million, which is why they did use witness complexes in order to make the computation faster. So some additional things that one did. Oh, and by the way, this sort of taking patches, a group, Arsuega et al., did actually analyze breast cancer data using a completely different technique, but it was kind of related to taking these sort of patches as well. So these ideas, I don't know if they got this idea from this. They actually got the idea from a mathematical idea instead, but maybe in the back of their mind, this might have, been there. There is these looking at points that are close to each other might actually give some interesting stuff. There was a lot of processing done to this data. One of the processing that they did is they normalized the mean intensity by subtracting off the mean. So, for example, this one, which is a very dark patch, if we subtract off the mean, then the lighter stuff will become white, the darker stuff will become a lighter gray, and so now we have something where the mean intensity is considered to be 0, where the mean intensity would be some medium gray value. So that's the first thing they did, is they normalized. That also means that we're now living in 8 dimensions. Before we were 9 dimensions, because we needed to know what each of the 9 values were to determine our patch. But now I can say this one will be determined by the remaining 8, since I need the mean to be 0. And so we basically created this equivalence class. So this is one way of sort of compressing your data, doing a projection, where I've now compressed all of the patches that if I just turn the intensity knob, I can make this patch darker and create this one. I can make this patch lighter and create a lighter one. So we can go ahead and turn our intensity knob to create a variety of different patches. We're going to put them all in the same equivalence class. So that's one thing one frequently does in data, is to do a type of projection, and this is a type of projection. We've projected into 8 dimensions now by just turning our intensity knob, projecting anything to mean intensity 0. We're going to do another type of normalization, and that is by dividing by the d norm, so the norm of everything will be 1. And so now if I calculate the length of this, so there's lots of different norms, so I'm not going to define the d norm. It depends upon which matrix you use to define this d norm, and there are different choices. You can see the paper for a little bit more information. So we divided by the d norm, and so now we get something where the norm is all the same, and now we have something 7-dimensional, and since the norms are all the same, we basically have something that's equivalent to the 7-dimensional sphere. Depending upon which metric you use, you can either call it an ellipsoid or a 7-dimensional sphere, depending upon which metric you're using. We can then renormalize to say we now have a 7-dimensional sphere. So now all our points basically lie on a 7-dimensional sphere, and we'd like to be able to look at that 7-dimensional sphere and say, well, maybe our data, after all this projection, doesn't cover the entire 7-dimensional sphere. Where does it live on this 7-dimensional sphere? Well, it lives everywhere on the 7-dimensional sphere. So this is the part where you think you might want to give up because you got everything. If you project and you get everything, you don't have any useful information. You're hoping that you project and maybe you just got, a diameter, an S1 or something nice living on this, S7. But every point in S7 is actually close to some point in our normalized data set. They also did other normalization, I forgot to mention, to remove some noise, but we will talk about removing noise probably after the October meetings. So you get really disappointed because now you don't have a paper to publish, but you get a bit more creative and you think about, well, their density is going to vary a lot from region to region. And so if you look at the points that are very dense, then that can give you some information. So the goal that they chose to do is look at the densest regions. So a common thing to look at is codensity, to look at the densest regions, and you can vary what you mean by density by varying this parameter k. So for this parameter k, we take a look at the kth nearest neighbor. So if I have, say, I'm interested in this point here, And let me create a few more points here, and we'll put each point a little bit further away than the next. Suppose these are my 6 data points, and I only have 6 data points, and I'm interested specifically in the first point I drew, this point right here. Then I can measure this distance. So I'll measure the distance to the closest points. And if I want to know delta sub 1 of x, it would be the distance to the closest point. Delta sub 2 of x would be the distance to the third closest point. Delta sub 3 of x would be the distance to the third closest point. There might be more than one third closest point, but we just want the distance. Delta sub 4, fourth, delta sub 5, the fifth closest point. I'll draw that line in because that's the line that they drew here, was the point that's the fifth closest point. So that becomes your delta sub k. If my delta sub k, if this distance is large, then I would imagine my x is probably sparse because I have to go further and further away. Now it is quite possible if I added just a couple more points, if I added a couple more points, some points that are very close to here, then maybe my delta sub k is actually small and the 6th point could be very far away. That can happen. But if you do this for a number of different points for a number of different k's, it does give you an idea. So we've got sparse if our delta sub k is large for the most part, and if it is small, then we assume it's dense. Again, it would be dense near this point, but again, it could be that the 6th point is really much further away, so it doesn't guarantee density. But on average, for the most part, this should work that a small delta sub k will meet a dense region. And then we calculate, so our data set is going to be the t densest points as measured by delta k. So in other words, if your delta k is small, then that's a denser thing. So we're going to take all the points, the t% points with the smallest delta k. So we get to choose 2 values, both k and t, and then we will choose the t% densest points, so the ones with the smallest delta k. And then after k and t are fixed, so you fixed k and t, then we can take a look at the persistent homology. And remember, with the persistent homology, we grow epsilon balls. So we grow these epsilon balls when we do our persistent homology to determine when we join things. So we throw out all the points that are not dense, and then we take our epsilon balls. Notice, by the way, that we've got 3 variables, our epsilon and our t and our k. So later this week or Monday, we will talk about multidimensional persistence, where instead of just varying epsilon, we can also vary t and k. But for this paper and for today's talk, we will do various different k's and t's, but for each example, our k and t will be fixed, and then we will grow our epsilon ball, so the persistence will be with respect to epsilon. Any questions up through here? Okay. So these are the various different data points that we have. If our k is 15, and we take the top 10% most densest points, and we project onto the first 2 coordinates. So remember, we're actually living on a 7-dimensional sphere, but we will project to the first 2 coordinates. We can see that we don't get everything. If we were to project, we actually should have gotten the entire disk if we had taken our entire data points. Although we would imagine that points in here would be less dense, but if we take the 10% densest points with our k equaling to 15, this is pretty much what you get. We can also do k equals to 100 or k equals to 300, and you can see that you get different things with the cut of 10%. It isn't until our k is 15 that we start choosing more of these points to get a circle. We can also do k equals to 15 or k equals to 100, k equals to 20, so the 20% most densest point, or the 30% most densest points. And so you can see the different pictures that one gets. And so we can study the topology of all of these diagrams and see what comes out. So that's the next one, is doing the persistence on each of these pictures, but now in our, with all our data points that are living in R9, although they're actually now less than, no more than 7-dimensional after all that normalization. But if we now do the persistence, and this is the 1D persistence, so we have the H1 is what we're looking at, or T1 with Z2 coefficients. And you can see that in some cases, we just get 1 bar. In other cases, we get 1, 2, 3, 4, 5 bars, and some of them persist for longer. And so depending upon your choice of your K, as well as the choice of how many densest points do you want to choose, that will definitely affect the topology. But one thing to keep in mind is that when we're doing these things, we do have a sort of embedding within here in terms of the sort of things that we're choosing. So we do have, we go back over here, this lives in here, if I take more points, then I'm going to have more points, and so this will be a subset of this. Here, we are now taking a look at points that are less dense, but we are still going to get the ones that will be, so we'll have larger delta Ks, but we'll still be having these sorts of things in terms of, I switched to the next page, but that's okay. Let's take a look at now a few specific examples and see if we can analyze what these H1s mean. So you can find your homology, but it's nice if you can actually trace back and say, what actually are the representatives, what are the cycles that gives us this homology. So if we take a look at, let's take a look at this first one here. This is with our K equals to 300 and our 25% most densest points. And so we've got about 5,000 points. Then our homology is just this one circle. So we only have this one circle. Now, when I say one circle, because we're doing Z mod 2 coefficients, we should be a little bit more careful about what we mean by a circle. But with Z mod 2 coefficients, we do have an actual circle. And it is this circle that if we take a look at a points along the circle, say I take a look at this point along the circle, then the patch that corresponds to it is at 3 by 3, where the first column is all black, the second column is gray, and the last column is white. Versus if I take a look at the point here, the point that corresponds to this is white in the first row, gray in the second row, and black in the third row. If I take a look at this, we have something that's actually between the two. We can see that it's black along this diagonal, gray along that diagonal, and white along this diagonal. So in other words, we're basically taking this thing, and if you rotate it, so if I start rotating this image, we can see that now I've got white here, gray here, and black here. So if I rotate in the clockwise direction as I'm going counterclockwise, then I get my next image. So rotate this one 90 degrees clockwise, and I'll get to this picture. Rotate this picture counterclockwise 90 degrees, and I'll get that picture. So you can see that's what you're getting along this primary circle. And you can also think about what you'd expect to see in terms of images. When you take an image, just look around the room that you're sitting in. I can see some horizontal lines. I can see lots of horizontal lines because I'm in a room with lots of computer monitors. And I can also see some vertical lines too, but some of the lines are diagonal because the computer monitors are lying, not at a right angle to the ground. So we can see lots of right angles, we can see some diagonals, and so that makes sense if I go back in terms of this was k equals to 300 and t equals to 25. So k equals to 300, it'd be something around here. So we'd be getting one of these particular pictures. And it makes sense in terms of your pictures that you get more of the more of the vertical, so these are the vertical ones, as well as the horizontal, and then a little bit less of the diagonal ones. So this makes sense in terms of what you'd expect to see. Notice I cheated a little bit here because here I'm projecting onto the first two coordinates instead of, but it works. Let's also take a look at our k equals to 15. So we'll still take our 25% most densest points, but now because our k equals to 15, we're looking at the denser regions. So we're restricting to some of the denser regions. In this case, we can see that our Beatty one is 5. It looks like we would have 5 circles. And so it looks like we have 5 circles. And that's what this picture is over here. I've got my black circle here. I also can divide that black circle, and I've created 2 circles. Divide it again, I now have 3 circles. Add this circle, I have 4 circles. Add this one, I have 5 circles. And so this picture right here, there's actually 5 circles that are linearly independent. So those 5 circles, just take any one circle that you want. So I started off with a black circle, but I could have started off with the green circle, and then add something, and we get one more circle, one more circle, one more circle, one more circle. And so we do have actually, I should say loops. So we have 5 linearly independent loops, but it actually looks like 3 circles, so it's the 3-circle model, but that actually gives us 5 loops in terms of our homology. Any questions about that? So let's take a look at our 3-circle model with our 5 loops. In this case, we still have the primary circle. So the colors are just to denote the intersections. These circles intersect. So if I go back over here, you'll notice the black and the red circle intersect at 2 points. The green and the black circle intersect at 2 points, and the green and the red circle do not intersect at all. And so that's what you see over here in terms of the coloring. We've got our red circle, which intersects the black circle at these 2 points. And we've got our green circle, which intersects the black circle at these 2 points. So this is the top circle is the same black circle that we saw before, where we just had a bunch of vertical strips that we could then rotate to get other types of things. And so that's what we have with respect to this. In our secondary circle, we have it intersected with our vertical strips. But what happens with our vertical strips? These are, again, all black and white. So I really have black, gray, and white. Well, notice I can then do permutations of the black, gray, and white. So I can switch the white and the gray, and so if I go this direction on my circle, the data point corresponding to this point right here, I've switched my white and my gray. Here I can go ahead and make my gray black, and then make my black gray, and then make my gray white. So it's a way of going from these verticals, which black, gray, and white, to white, gray, and black by changing, the columns slightly as you rotate along here. So as we rotate along here, we are trying to get from this one to this one, which means we need to make the white one grayer, darker, and we need to make the black one lighter. And the middle one just needs to become, it could have stayed gray, but it still went through these things here anyway. So that's what they found. Instead of going through gray, gray, gray for the middle column, it went gray, white, 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 gray. And we've got the similar thing on the other side. It just now it goes gray, black, black, black for the middle column, and then the white one gets darker, and the black one gets lighter. And you can see the same thing, a similar thing happening on the secondary circle. It's just now we're starting off with this is the one that intersects. So we've got black, gray, and white, and then our black becomes lighter, our white becomes darker, and our gray goes black, 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 back to gray again. So we can see that on our circle, each of these points, they are close to each other, so we can see that this point and this point are relatively close, and we can travel along these close points to go ahead and create our circle. And so we have a nice three-circle model. So any questions on that? But we would like to know, do we have any surfaces in here? So they studied this a little bit more, and they found some interesting gluing patterns. I'm going to leave out some things so that we get to cover more than just this paper today. And so here we've got that five-circle model. It looked like if you were to fill in those circles with a surface, that you got something interesting. So they played around a little bit more. And to play around with all of these things, remember we had a lot of points, so going ahead, if you want to have lots of points and run lots of different scenarios, that's where you might want to do the witness complexes so that you can do lots and lots and lots of different scenarios. So I've motivated my Wednesday's lecture as to why we want to use witness complexes. But this is now, we use k equals to 100, t equals to 10. Notice our Betty 1, we have some interesting stuff for a while, but eventually we just get, something here. But now our Betty 2, it looks like we've got, this kind of thing here. And we do have just, sorry, I went the wrong direction. Betty 0, we have just the one component, so just one component for Betty 0. For our two components, for our Betty 1, we have two circles. For our Betty 1, we have two circles. And for our Betty 2, we have just one, two-dimensional cycle that will persist. So let's take a look at this. Does anyone remember any, first off, before we look at that, does anyone remember any complex that has this kind of homology? Betty 0 being 1, Betty 1 being 2, and Betty 2 being 1? Well, there were lots of things, and I just lost my arrow. Somehow I went to, okay, there. My arrow's back. We have something where we can glue things. So let's take a look at the black circle. Oh, the things changed color here a little bit, so let me find my circles again. My black circle is actually the red one now. So there was a change in coloring, so let me actually choose my black pen. You can notice we've got our vertical patches here. They're still the 3 by 3 square patches, but for simplicity, we cut off a little bit. You can see that we are rotating as we're going around here. So I take this 3 by 3 patch, I rotate it, rotate. And so this right here is my black circle. So that was actually my black circle right here. Note, right here I've got white, gray, and black in a diagonal conformation. Where else do I have white, gray, and black? Oh, over here. So this edge here, if I put an arrow on it, is going to actually match up with this edge over here. So look just at, ignore the surface at the moment, look just at the red line. I've drawn my black circle in two pieces. I drew the black circle here, and then I jumped over and I continued doing the black circle, and you'll note as I go to this point here, black, gray, white is black, gray, white, and so I just cut my black circle into two pieces, and you get the black circle back if you glue this piece to this piece and this piece to this piece. We're topologists, and so instead of drawing a single black circle, we went ahead and we cut it into, at two spots, and then drew it here and here. But if I glue it back together, so we will say that this is glued to this and that is glued to that, we get our black circle back again. We can also take a look at our red and green ones. I don't remember which was the red and green, so let's just assume yellow is red. And so we do that. Everything is vertical, so everything is vertical right here, but we do have a change in the colors. And we can see it intersecting with our black circle at these 2 points. And then this one here, this circle here, this patch here is identical to that patch right there. And so we would glue this circle, this point here to that point here, creating what was probably our red circle. I think the red circle was the vertical ones, hopefully, maybe, yeah. And then we've got our green circle, which is actually green. Again, this point here is identical to this point here, and so we have our green circle. And so that's our green circle. By changing our T and our K, we are able to actually fill in this surface right here. So we can actually fill in this surface. So notice we've got more points right here. We didn't look at this one at all, this circle right here, but this is another point which is not identical. So it's basically similar to these, but you can imagine, how do I get from here to there? I just start rotating, because remember, if you travel along the black line, you just rotate. So if I want to fill in the surface, we can go ahead and fill in, let's go ahead and fill this thing right here. You can easily fill in that surface by just rotating everything. So going along here and taking my red-yellow circle and starting to rotate the data points, and I get to this new circle, and I've now filled in this entire thing right here. I've now filled in this surface here by just taking my patches and doing different rotations. So you've got fix this, rotate 5 degrees, 10 degrees, 20 degrees, up to 45 degrees right here. If I take a look at just this surface right here, notice that this would all be equivalent to this. They're all identical. And so I can now glue this to this, and I get a cylinder. So I had my yellow-red circle, and I had my other circle corresponding to this thing right here. And if we fill it in with a surface, we get a nice cylinder connecting these things here. If we continue our rotation, we can now continue filling this thing in here. So we can continue, getting out our cylinder right here. So we now have rotated a full 90 degrees going from here to there. Continuing to rotate some more. We can continue to rotate, so we fill out our cylinder more on this side, fill out our cylinder more on this side, so we'll fill in this thing here, rotating a bit more in this direction. So we continue filling out. And so now we have one nice long cylinder. Oh, not really, because I filled out so much that I now have, remember, this edge, this entire edge here. Let's actually get a different color. So we have this entire edge here, this black circle, which I'm now turning blue, so we've got lots of things that are two different colors. This, so this blue one, this is not black, this is a blue circle. That's the same as this blue circle over here. So I've got this blue circle is the same thing as this blue circle. But there's two ways of gluing those blue circles. In one way I get a torus, and the other way I get the Klein bottle. And you can see in terms of the gluing, because this point got glued to this point over here. So this point here got glued to that point over there. Then when I do this, I'm going to be gluing them in the opposite orientation. And so in other words, I will clean up my picture and say that we've got a Klein bottle. And so there's actually a Klein bottle in this data, and you can actually see what that Klein bottle means. You can see what that Klein bottle means in terms of, rotating your patch as you go along here, and then it comes back along here. So you can see what the data points along. So if we go ahead and take a look, put a patch on this, maybe I will do a bunch of vertical things. So I've gone ahead and chosen one of these patches here, and I can see as I rotate it along where it's going to look, what it will look like. So we can actually see this Klein bottle and what it means in terms of our data. So that's one thing you can consider doing as well. This was not easy. So figuring out where the Klein bottle was and what it looked like, that took a bit of work. And to create the surface was changing the various K's and T's to actually see this stuff. But once they had, they did change the various K's and T's to see that they did get a Klein bottle, but they were actually looking for a Klein bottle. The reason they were looking for the Klein bottle is because they had this three-circle model of the red circle, the green circle, and this black circle. And by looking, if you take a look at the red circle and the black circle, and you only put that in the rectangle, it screams Klein bottle. Try to fill in the surface and find the Klein bottle. So before they even saw the Klein bottle, before they saw the Betty 1 equal to, the 1, 2, 1 in terms of the Betty 0, Betty 1, the 1, 2, 1 in terms of Betty 0, Betty 1, Betty 2, they figured there might be a Klein bottle, because if you draw this, you kind of think, oh, how would I go from red circle to green circle, my red yellow circle to my green circle? If I do this rotation, and if I continue this rotation, I fill up the surface and I get a Klein bottle. So they expected to see a Klein bottle. So by analyzing these things, you can, see a few things as to what you expect. So that's basically what we will talk about the paper for this, the Carlson et al. Paper today for the image data. Any questions about the image data before we talk about creating complexes? Any questions? Okay. We will create simplicial complexes. There's lots of ways. We start off with our data points. All we really need to know is the distances, because once we know the distances, we'll frequently use these balls around. So we can use these balls around to denote the distance. So if the two balls intersect, we know that they're close enough, and we can now create our edges. And so if the balls intersect, we create our edges. And we now have our one-dimensional edges. We can then go and create our simplicial complex via either the rips and create the flag complex or the clique complex. These are common terms, so that's why I mention it. We've got our flag complex, our clique complex, where we basically add all possible simplices. So the Viator's rips complex is the type of flag complex, which is also a type of clique complex. You're basically, a clique is where all your vertices are connected by edges. So I've got a clique right here, and so I get my clique complex where I now create my highest possible dimensional simplex, throwing everything in, also called a flag complex. But we could instead do the check complex. In the check complex, we're doing the nerve. I forgot to type up that thing here. I meant to add the word nerve, but I will just say it for now. In terms of that, we just look at where things intersect. So in our nerve, we're only interested in where our balls intersect. So if our balls intersect, then we create our simplex. So in this case, the balls intersect, so I have a nice triangle simplex. Here, the balls don't intersect, so I don't fill this out. All the other ones, all the balls intersect, so we have the same thing that we had for the rips because everything intersected. But in here, since we didn't have the 3 balls intersecting, I did not get my 2 simplex. So we only get a k simplex if we have k plus 1 balls intersecting. And so we've got our check complex, which was the nerve of putting these things in if and only if. And the nice thing about the check complex and the nerve is that it preserves our topology. So sometimes you actually want to see that nerve. Sorry, sometimes you want to see that hole. So if you want to see that hole, if you want to preserve the homotopy, then you might want to have the check complex. But when you're doing data and you're growing your epsilon balls, usually the RIPS complex is just as good, because if I just grew my epsilon balls a little bit more, if I grew my epsilon balls a little bit more, we would have gotten the RIPS complex. Okay. Now I'm going to work with fewer points, not because I'm doing witness yet. No, I'm not doing witness yet. I'm working with fewer points because I'm creating a Delaunay triangulation via Voronoi diagrams, and it would be too much work to do all those other points. So we're only going to do it for 4 points. We're first going to calculate the Voronoi diagram. And this gives me another type of, one of the things in terms of my check complex is I had all of these, this was a lot of data points. If I know, for example, that my data points lie in the plane, maybe I don't want the higher dimensional complexes, and instead I might want to work with the Delaunay triangulation instead. And so we do that via the Voronoi diagrams. We fix a vertex. I'm going to fix this red vertex here and create the Voronoi cell, which is basically, I create a lot of half planes. All I want is all the points in X that are closest to V. So if I do that, basically, I want the points that are closest to my red point here. So the points on this side are closer to the black vertex. The points on this side are closer to the red vertex. So I'm going to want to create all the, in my Voronoi cell associated to my red vertex V, I want all the points that are closest to V. If I take another hyperplane, I might be in higher dimensions, so I can take a plane. In this case, my plane is a line, because I'm in 2 dimensions. And I want the points that are just closest here. I can take another line here. I want the points that are just closest here. And so we have that on the next thing here. We take all those planes, pretend that they basically, if I take the line between these, this line is supposed to be the perpendicular bisector. And then I shaded in the part that was on the red side so that I would get the closest points here. And similarly, if I do the perpendicular bisector for between these 2 points, and I shade in the side that contains the red vertex. And similarly, we do the perpendicular bisector for my last one here. So we just take the perpendicular bisector of this, and we take this here, and then what we're interested in the Voronoi cell would be the intersection of these 3, and the intersection of those 3 would give me this thing right here, would give me this region right here. And so that intersection, so on here, if I go to the next one, our Voronoi cell would be, corresponding to the red, would be this entire region here. That would be the Voronoi cell. We can do this for lots of the other ones, so now I'll let this one be the red point, and I'll get that cell, this cell here for this red point. So I get this cell for that red point. We can then do it for the next point, get another Voronoi cell, so now I get this Voronoi cell for this one right here. And if I do it for the last one here, we can see that we have this Voronoi cell. And so now we have the Voronoi cell at which point we can then, so this is the Voronoi diagram, actually this is the Voronoi diagram right here. We can then calculate the Delaunay triangulation by doing the dual. So for each cell, I get a vertex, and then if the things, I'm now doing the nerve again. If my cells intersect, I draw edges. And if the three cells intersect, the three cells do intersect right here. So I'll now fill in this triangle. And then they intersect here as well. They intersect here. And then I also fill in this thing here. And so if you take, we're doing the nerve again to get the Delaunay triangulation. But now, because I've chopped off my balls, we now have fewer things, and so that is our Delaunay triangulation. So we will talk more about that next time, along with alpha shapes and witness complexes. But this Delaunay triangulation is one way of getting fewer edges in the check. You can sort of imagine that these things are sort of acting as witnesses. So it's sort of the witness complex is sort of an extension of our Delaunay triangulation. So sorry for going over today. Any questions before we head off? Well, thank you. I'll see you on Wednesday.